Okay, so going over the questions from homework number 20, starting with number 1. They're trying to trick you with this first one because you're used to thinking, hey, that's 2. Because you look at it and you go, the limit as n approaches infinity is 2. But realize that is for just the term itself. Your final term is heading toward 2. And this actually is a diverging series by the nth term test for divergence. You can see that 2 and 3 are both geometric because your n is only existing in an exponent. And let me just kind of show the contradiction with n is not in an exponent on that first one. So you need to figure out, do they converge or diverge? So the first thing is, what is R? And R is whatever has the n exponent. So you might be able to quickly see that -3 in the denominator is the only thing that has the n exponent. If you don't see that R is -1/3, you can plug in n equals 1 and then plug in n equals 2. And if you divide any term by its predecessor, you will get that R. So for number 2, it is converging, but the question is, does it converge to 2? In order to determine that, I need my first term. Always be very, very careful with geometric series because sometimes it starts at 1 and sometimes it starts at 0. And that's really where people make their mistake. If I plug 1 in, I find that my first term is a positive 8/3. Then I throw this into the geometric series formula of first term over 1 minus R. And a little bit of arithmetic later, you can see that this is 2, 8 divided by 4. So this does work. Now the question is, does number 3 work? So again, what is R? R is 1/2. So it converges. What is the first term? Plug 0 in. When I plug in 0, I get 1. And then the sum formula is first term over 1 minus R. And that is also 2. So the 2 and 3 only would be the correct answer. Now with number 2, it wants to know the value of p that will allow this to converge. What you're expected to notice is this +1 is screaming, I need a comparison test. I have to be compared. This +1 is a problem. Anytime you see addition within the numerator or denominator or subtraction, most likely you need a comparison test. And you might realize that you need to compare it to n over n to the p power. Now we're only wanting to know for converge. So let's see if direct comparison test will allow me to do the converge. My series is n over n to some power plus 1. If I'm adding 1 to my denominator, that forces my overall fraction to be smaller than the one that doesn't have the +1 in the denominator. And I want to know when I converge. So that means I need to look at when does this converge. because mine is going to be smaller than whatever that is. And I want to add a reminder that we have to have positive terms only to use the comparison tests. So once you realize you need to compare it to n over n to the p, then you want to use your exponent rules. Now in this kind of situation, I prefer to use my exponent rules backward. In other words, the bottom exponent minus the top exponent creates the bottom exponent. And then from there, it's annoying that they used p because you've got to turn to p series. But whatever the exponent is here, according to p series, this will converge as long as that exponent is greater than 1. Once you have the inequality, add 1, and you find out that this will converge as long as p is greater than 2. It will diverge with equal to 2. If it's equal to 2, then it will be comparing to the harmonic series, and it's not an alternating series. And on top of that, in alternating series, make sure you understand you cannot use comparison tests on an alternating series. However, I'm going to show you a way around that in a couple of days, which may or may not work in a given problem. So, yeah. And now the integral test. Now, what this actually, in a way, does is it takes us back to the improper integral. But if we understand the p-series test for series, then we understand that as long as this exponent is greater than 1, we will get a converge. And that gives us that p is 1/2. Now, mind you, it has to follow all the necessities of the integral test. Because if I'm using p-series, then I'm thinking about sigma. But of course, I could integrate instead. But if I use the integral test, all I need is for that formula to be continuous, positive, and decreasing. Continuous, positive, and decreasing. And it is with x values that are from 1 to infinity. So that gives us that it will converge if p is greater than 1/2. Number 4 is definitely integral test. And it even begins with telling you that your function is positive, continuous, and decreasing. And so be careful. It is telling you that the sigma is converging to k. Make sure you're clear that if you remember what it looked like when we did the integral test, and I'm going to run over to the integral test and find that picture. The area under the curve and the area of these added rectangles is never going to be the same thing. Well, never say never. There are always exceptions to the rule. But basically, they shouldn't be expected to be the same. They should most likely be very different. So when I come back over to the problem, I want to realize that it's not saying that the integral of this function is equal to k. It might be approximately k, but it is not equal to k. So that kind of takes out these two that I shouldn't, even for a partial sum. Actually, no, this is not a partial sum. If I cut the integral off for some n, it's still not necessarily going to be exactly that k number. So you know that if your integral converges, then your sigma also converges, and vice versa. That is an if and only if situation. So that means if your sigma converges, which you're told it does, then the improper integral converges. And that's where we get that D has to be correct. We know C is out. And then on letter A, that's really problematic because that's saying the term itself, which should be heading to 0 if we're going to be getting converge. And I want to make sure to clarify, this said which of the following must be true, to emphasize that even if we have some exception to the rule, B and E are not things that must be true. In fact, it's likely not. So with number 5, we've got ratio test. Woohoo! Who's excited about ratio test? With ratio test, I'm plugging in the n+1. And I'm dividing by the nth term, which is the same thing as multiplying by the reciprocal of the formula. I have to have in front of this limit as n approaches infinity. And then you can start a little bit of algebra. So I'm just going to set this to the side to clarify. E to the n+1 is e to the n times 1 more e. n+1 factorial is n+1 times n factorial. And I get some lovely cancellations. And I end up with, I need to solve the limit as n approaches infinity of e over n+1. E is a particular number. If my denominator is heading to infinity, this is 0. If you're in a free response situation, you want to emphasize that because this answer is less than 1, we get converging by the ratio test. And then taking a look at the possible answers, we definitely needed to simplify to see that D was the limit we were solving. And then one last problem. We want to know the value, and it's a geometric series, although it does give us the possibility of diverging. I notice it's a geometric series because the variable is only in an exponent. I can always rewrite this as 2 to the n times 2 over 3 to the n to see more clearly that my formula is showing that n is a power on 2/3. 2/3 is the r. I need to make sure that I find my first term, take a good look. I'm starting at 1, plugging in 1. I get 2 squared over 3, so I'm getting 4/3. Then my sum is the first term over 1 minus r. Oh, Scam Likely is trying to call me yet again. And so that winds up simplifying to 4. And I believe that was the last problem. Yes. So I'm going to stop recording if I can find it. There it is.